Okay, so hi all. So this is the, third, maybe? I think so, third video in our Laplace chapter, or section. And here we'll build on what we did, I think, in the last video, which was to get some more examples and experience using transforms to solve actual ODEs. So I think I did a few examples at the end of the last video, and I'll do a handful more today. And we'll expand our knowledge, I guess, or familiarity with the chart by introducing a couple of other rules that are in the chart. Actually, let's do that first. Oops, I hit the wrong thing. So if you have the chart, hopefully you've maybe found a functioning printer, or or at least can pull it up from Canvas if you'd like, or you could just, I don't know, gosh, if you don't have a printer, you could probably actually just hand write this, right? I mean, this isn't like the world's longest chart, so if you want a paper version of this, which I gotta say is pretty handy, please feel free to do so. So here's the chart. Last week we used the first five, or got to know the first five pretty well, I think, or at least used them. So who else is in the chart here? So we're gonna, in this video, I'll start showing you how to use 6, 7, and 8. So let's look at them first. We'll come back and I think I'll do a little proof of 8, of which 6 and 7 is actually just a specific version. So 8 is really the rule, but 6 and 7 come up so often that usually charts list them separately. But so let me, I'll start there though, and actually talk about 8 first. So if we look at 8, right, what does 8 say here? So 8 says, I don't really need to think this. So 8 says what? So 8 says if you have e, so this is on the left side. So if you have a function that you're looking at and you want to do the transform, and it happens to look like e to the c is some number, e to the ct times f of t. So what does the f of t mean? F of t means it's probably one of these guys, or in theory anything in the chart, but probably most likely it's one of these first 5 guys. So in other words, if you have e in front of some function, that's what this rule is trying to tell us how to do. Right, so some regular function, again, maybe one of these 5, but you actually have an e in front of it. Then if you wanted to do the forward transform from left to right, you wouldn't worry about the e piece. Instead, little f, we know little f turns into big F. Now, I can't ignore the e piece, so what does that actually do for us? So if you have little f, you could do big F. Now, big F would be big F of s. So the only difference is that over here, if you have an e in front of it with a c up in the exponent there, then you do this is what we would call a horizontal shift back in pre-calc. So all I'm going to do is I'm going to say, well, I'm going to compute big F. But rather than writing down big F of s, I'm going to do big F of s minus, 6, okay, whatever c happens to be. Okay? And if you look, you don't use 8 a whole heck of a lot, except that 6 and 7 are 8, but with rules 4 and 5 in place of f. So in other words, of course, if you look at this, right, 8 says you could have e with any function, whereas 6 and 7 say you could have e with these 2 functions. Okay, so since they come up so often, here they are, and we'll use both of these today. So let's just read these so we at least have some sense of what do these look like. So if you have e with sine or e with cosine, now that should look familiar, right? We know that from solving ODEs, we know that when we have complex roots, right, with i's in them, we know that we essentially get this and this, right? In fact, these are the 2 solutions, the 2 homogeneous solutions to a second order ODE that has imaginary or complex roots. So it's natural that these are probably going to be in our story since we're still solving ODEs. So if you have either one of these, what do the transforms look like? They look like these. Now, of course, the most important thing I'm going to point out to you in this is that the bottoms are the same. So if you remember from last week, the biggest challenge is not reading or using this chart from left to right. The biggest challenge is reading this chart or using it from right to left. So we're going to see in a few minutes when we do our examples, we're going to see stuff that looks like these 2. So the biggest thing to remember is that, first of all, the bottoms are the same. So as long as I can make the bottom, if it already looks like this, or if I could make it look like this, I could probably figure out how to finagle the top. So again, it's usually the bottom that you need. And the only difference between 6 and 7 is that 7 has an S on the top and 6 does not. Okay, so if you end up with the bottom looking like these and you have an S on top, then you're going to have to make it eventually be rule 7. If you don't have an S on top, you're going to have to make it eventually look like rule 6. All right? And of course, in order to make this work, if you're doing 6, you need whatever the b happens to be, you have to have that on top. So if this is b squared, then you need a b up here. And then in this case, for cosine, whatever a is, right, s minus a, if that's s minus 2 squared, then you'd need an s minus 2 on top. So this is going to lead us to some, what's the right way to put this? Having to do a little bit of creative algebra sometimes to get these just right. All right? So we'll see this though, but keep these in mind as we go through this today. If you look at the bottom of these, maybe this reminds you of an algebra trick known as completing the square. I think you all did this at some point, but it's conceivable that this was like a really long time ago that you might have done it. And if you've never seen it before, I'll show it to you today. All right, so I think we'll say goodbye to the chart for now. And I just will take 30 seconds to remind you that the idea of solving ODEs with the Laplace transform, of course, is that I start with a regular ODE that we've been looking at all semester. I take the forward transform using the chart, reading it from left to right. I get a whole bunch of stuff over here. I have to just use basic, pretty basic algebra to make this turn into, to make the stuff I have over here read Laplace of y equals some stuff with s's. Now this is the hard part, is the last part, is that each of these terms, however many you got to figure out a way to do what we call the inverse transform, which is you and me, reading the chart from right to left, which means I got to get it just right in order to be able to read from right to left. And that's what I'm going to show you today, are a couple of other tricks to move you towards getting it just right. All right, and if I could do the inverse of each one and write them down, that's the solution to my ODE. So we did a few examples, which I'll just be blunt with you, were kind of on the easier side. So we did this one, which we already knew the answer to, but that was pretty simple. This one was a little, there was a little bit of intrigue here, I guess, but this was also pretty simple. So how does this become not simple, right? That's always our question. How does this become difficult, right? So it becomes difficult mostly just in that in order to go backwards to do the inverse transform, you end up not quite having something in the top 5 group on the chart, 1, 2, 3, 4, 5. Those are like pretty good. But if you have something not quite that, we might need, for example, 6, 7, and 8 that we just looked at a minute ago. That'll help us do shifted versions, essentially, of those top guys. And even there, though, getting them to look like that, they were a little bit specific, right? The more complicated, or the more terms you have in what you're looking for in the chart, the more you're going to have to do some rigging in order to make it work. So here are 2 algebra tricks, I think from your past, but if they weren't in your past, they are in your future anyway. And you're going to use these on probably most problems, except for really easy ones like these, just that we did in the last video. So 2 algebra tricks. And I'll tell you how these sort of fit together. One is called partial fractions, and the other, as I mentioned a minute ago, is called completing the square. So I think we did partial fractions. Partial fractions is something I think you've all seen. And I think we did it in Calc 2. I'm having memory, a difficult time remembering. It was a year ago. Most of us were in Calc 2 together, I think. But some of you others have taken Calc 2 at some other time, or some other place maybe even. But I think we did partial fractions to help us do integrals, which is the same kind of idea that we're going to use here, at least in terms of why we want to use it. But if we don't know what this is at all, if we've never seen this, here it is. So for partial fractions, what's the idea? So if you have a fraction of polynomials, and in particular, it looks like this. Now I'm going to do this with s's, because of course we're going to our world is t's and s's, right? And our algebra world is mostly once I've done the transform. So I'm going to mostly have s's in our lives for the next couple of weeks. So I'll give this to you with s's instead of x's as we probably normally would. So if you have some polynomial that has s's in it on top, and on the bottom you have 2, you could really have more than 2, but let's try to not totally kill ourselves here. You have the product of 2 polynomials. Again, I'm using s because that's our variable, but normally you could say x if you'd rather. But so what am I saying here, right, is that you have a fraction. On the top you got some polynomial that has s's, and on the bottom you have the product of 2 polynomials that have s's in them. And of course by polynomial I just mean powers of s. Then if you have this, and I'll say a little bit about what has to also be true, but the goal of partial fractions is to take something that if on the bottom, now this, how do you get these 2 things on the bottom? Maybe they're just already there, or maybe it came about because you factored, right? We know that when we factor we usually get, so I don't know, something like that, right? So it's possible that you've done a little bit of algebra to create Q1 and Q2, or it's possible that they're just already there. Fine. But if you have it like this, then a wonderful trick that you can use, or something you can try to make this work, is that you can split this into the sum of 2 fractions, where one of them is over the first piece, plus something over the second piece. Okay, we do this in Calc 2 when we did integrals, and when the bottom was hard, but factorable. Like if it was this polynomial, squared polynomial, if we factored it, we got 2 easier integrals out of it. I'm pretty sure we did this, but right? So the idea is that you can split this. Now, it'd be great if I could just split it and just say, hey, I split it. Well, no, you can't, right? You have to sort of do a little bit of an algebra problem in order to figure out how to accurately split this. So in particular, what goes on top? Well, what goes on top is I don't know, and I don't know. Oh, okay, right. So I get some polynomial on the top of the first one, I'll call that P1 of s, and I get some polynomial on the second one, let's call that P2 of s. However, if you remember the way that this trick works, is that the degree of the numerator is 1 less than the degree of the denominator in each of my 2 fractions over here. All right, where P1 and P2 are 1 degree less than Q1 and Q2, respectively. Right? So what goes on top of Q1 is it will eventually be a polynomial of degree 1 less. And ditto for Q2. A polynomial of degree 1 less than Q2 is going to be what ends up on top. All right, so of course if this is squared, so if that, for example, has s squared, then on top you're going to end up with an s to the first. In other words, a line, right? This is a parabola. That would be a line. Maybe this is the first power, right? Just an s, in which case that's a line. Well, you'd end up with something 1 degree less than a line, which is just a constant, just a number, right? So since I think we've all seen this, the way to do this, or the way to make this happen, so this is the goal, right? If you have a function of polynomial, you can write it. Oh, sorry, I didn't do a good job of. Okay, sorry. If you have a fraction of polynomials, that's what we start with. Then you could rewrite it like this. In other words, it's the sum of 2 of these, where P1 and P2 are 1 degree less than Q1 and Q2 respectively. And the trick for doing this is how to do this. Right, so I think the idea is that you want to guess guess that P1 and P2 are general polynomials of degree 1 less than Q1 and Q2, respectively. All right, so whatever I see on the bottom, I'm going to guess a general polynomial of degree 1 less on top. And then in order to actually do this or figure out, okay, that's nice, but in order to figure out P1 and P2, you're going to then get a common denominator, which is probably just Q1 times Q2, and add the numerators. Okay, so of course, in order to get a common denominator, you multiply the top and the bottom by whatever you need to. In essence, I'm going to essentially just cross multiply. So P1 is going to be times Q2, and P2 is going to be times Q1. That means I'm going to get stuff on the top that is the same denominator as what's on the left. So if I add across the top, I'll get something that's supposed to match the original over here. So again, I'm going to add the numerators, and then maybe I'll say organize and compare the sum. And in particular, organize by power of S and compare to the original P of S. And from there, you'll be able to solve for the coefficients. Okay, so it's actually a little bit like undetermined coefficients, right? Our strategy for solving. We make a guess and we plugged it in, and then we ended up with some letters. But then we did some matching, right? We organized by power of T, I guess it would have been then. And then we matched up the letters that had to match with whatever was supposed to be there, and then we solved for all the coefficients. Same idea, right? So it's very similar. All right, so partial fractions is a great trick, and the reason why we're doing this isn't just to torture us. It's because these are going to be easier. Each of these, you're probably going to be able to do the inverse of. But together, I have no rule that lets me say, lets me deal with what do I do when I have a product of two things on the bottom. I don't have any rule that handles that, so I'm going to need to do something like this. All right, so let me do an example of this, and then we'll get to our second algebra trick. And then I'll sort of pull it together here for you. All right, so let's try I double prime and y and 2y and 0. And y of 0 is 1, and y prime is 0. Okay, so that's our ODE. And we're going to try to do Laplace. Now again, this is one that we know, or we know how to solve already. Well, let's try it this way, right? We'll try it with our newfound trick here and see if we can make some sense of this. So let's go. So I'll do the transform of the left-hand side. I'm not going to write the whole thing out every time, so I'm just going to say by now we've done a couple. So the Laplace of y double prime, look it up in the chart. It's s squared times Laplace of y minus s times y of 0, which is 1, minus y prime of 0, which is 0. Okay, so that's the Laplace of y double prime. Now, again, you have to be careful that you remember, if I have a minus here, which I do, I have to probably, I want to maybe just double check that I don't mess this up. I need to do the minus the Laplace of y prime, which again, you can look that up in the chart. It's s Laplace of y minus y of 0, which is 1 yet again. Okay, and then the last one is minus 2, and then remember the negative 2 in front, that's just a coefficient, so it comes along. And the Laplace of just y is, well, the Laplace of y. Okay, and the Laplace of 0 is 0, so the right-hand side is 0. Okay, so we've done our first step, which is to take the Laplace of everything. Now I'm going to collect the Laplace terms on the left and everybody else on the right. So let's see. So who's got a Laplace of y? I have s squared. I have minus s. And I have minus 2. All right, so those are my terms that have a Laplace. The terms that don't have a Laplace, let me put them on the right side. So what do I have left? That's minus s, which when I put it on the right turns into plus s. And what else? That's a 0. And then I have plus 1, which when I move it to the other side is minus 1. Okay, so I think that's everybody. So now I've finished step, I don't remember which, how we were numbering this, but I've gotten this to the point where it reads Laplace of y equals. Okay, so once I get to this point of any problem, I'm hopeful that I'm able to do the inverse. I'm down to the last step, which is compute the inverse transform of what I see. So this is where I appeal to the chart and I say, oh, okay, well, I'd be very happy if I had something like this in the chart. Well, I can pull it up just so we can stare at it for a minute. So, well, let's see. Again, I think for the most part, these are all pretty much all fractions. So look at the bottom of the fraction, right? That's mostly what you want to try to match up. So we have s squared minus s plus 2. I forget what exactly we have, but something like that. So I need an s squared in the bottom. So that's out, that's out. That has an s squared, but it doesn't have an s, right? I need an s term. So that's out, that's out. Maybe. Okay, well that's it, right? So, so in terms of which of these might it be, well, I don't know. It could be this. Ooh, but that would require me to get awfully lucky that it factors nicely like this. Now I'm going to show you the trick to do completing the square in a minute. But what actually I might notice first, so keep this in the chart again in your head. I don't have any of these right now. But notice, and maybe you did notice, that hopefully your algebra instincts are calling you to factor the bottom, because it does factor. Now sometimes it's not going to factor, and that's when we're going to use our second trick, which is completing the square. But in this case, this does factor. And in particular, it factors into s minus 2 and s plus 1. Oh, okay. So if we believe what we just, what I reminded you of with this completing the square business, partial fractions business, I can write this as something over s minus 2 and something over s plus 1. Because I factored, right, this is exactly the sort of prototype for using partial fractions, because the bottom is the product of two polynomials. It is. So if you put those polynomials, list them separately, then the good news is that you can write it like this, or you're going to be able to separate this, where what's on top of each of these little fractions is a general polynomial of degree 1 less than what's on the bottom. The bottom of both of these is an s to the first, which means what's 1 degree less than s to the first is a constant. So I'm going to be able to write this as a over the first thing plus b over the second thing. And all I have to do now is figure out how much is a and b, and then allegedly that's going to be helpful in me getting an answer. So let me do that side problem. Okay, I'll do it over here, I guess. All right, so in order for me to have this work, I'm going to need that s minus 1 over s minus 2, s plus 1 is this. Now, in order for me to have these guys in order for me to be able to add these guys up, I'm going to need a common denominator, which is, of course, just this. So, so in some sense, I'm sort of saying take this top, multiply it by that bottom, so that the top and bottom both have an s plus 1, and this guy gets hit with s minus 2 over s minus 2. So I get a s plus 1, b s minus 2, and all of that's over s minus 2, s plus 1. Okay? So this is the same thing we did in like 3rd grade, getting a common denominator, and then you add across the top. Now the good news is the bottoms are now identical, which means the tops must also be identical. So we must insist that s minus 1 has to match, let's see, what do I have here? as plus a and bs minus 2b. So those have to match. Or I should say I'm insisting that they match. Well, now I just have to match up powers of s. So on the left-hand side, I have s minus 1. Over here, what do I have? I have s, or I have, well, it doesn't, oh, gosh, I lost my a there. I have s times, what, a plus b? And then what else do I have? I have a minus 2b. So who has an s on the right side is a plus b, and who doesn't have an s would be those guys. And remember, you have to match, right? So, of course, in theory, there's a 1 there. So that has to match that, and that has to match that. Okay, so just like on determined coefficients, I'm going to get a little system here that I can then solve. So what do I end up with? 1 is a plus b, and negative 1 is a minus 2b. Okay, and then use your favorite solver here. I'm going to subtract these. Because if I do that, I'm going to have a minus a, which is going to be good news, right? So here I have 1 minus negative 1, which feels like 2. And here I have minus negative 2 is plus, so I have 3 b's. So evidently b is 2/3. And then, of course, if b is 2/3, a is 1/3, and since they have to add up to 1. Okay, so you reasonably quickly can come up with the proper decomposition. And so in reality, this, right, a is really 1/3 and b is really 2/3. Oh, well, those can get filled in now. So I have Laplace of y equals a is really 1/3 and b is really 2/3. Now, I'm going to do this all in one step because I'm going to run out of space if I don't. I could put the 1/3 up here, and I could put the 1/3 in for A, and I could put the 2/3 in for B. But think about the chart for a second. The chart does have 1 over S minus A. That's rule number 3, I think, or 2. It's the E. It's the E to the AT. So rather than putting these numbers on the top, I'm just going to leave them kind of out in front. So I'm going to say that's 1/3, 1 over S minus 2, and 2/3, 1 over S plus 1. Okay? And the reason just being, remember, coefficients are my friend. I can deal with coefficients forwards, backwards, it doesn't matter. They always just come along. It's the other piece that I need to have just right. So if I look back in the chart just for one last second here, it's rule number 2, right? Rule number 2 says if you have e to the AT, that's 1 over S minus A. Well, if you look at what we have 2 of them, right? But we've got a couple of things that both look like this. So 1 over S minus A turns into e to the AT. Oh, that's pretty good for us, I think. Right? So I think, if I'm ready to go now. So I do the inverse. A coefficient always just comes along. So 1/3 is just going to come along. Now this is number 2. That turns into e to the 2t. That looks like a weird e. E to the 2t. And then the second piece, again, my 2/3 comes along, because that's a coefficient. And this is 1 over, remember, it's S minus A. So if this is minus A, then A was really negative 1. So negative 1 times 2. And that is the solution to the ODE. And this should look a little familiar, because that was what? This is our first case where you get 2 real roots. Now, would I recommend doing this problem with Laplace transforms in real life? No, right? Because, of course, this probably took, 10 minutes maybe. Whereas if this had been on the last exam, you would have probably finished it in about 2 or 3 minutes. Well, 2, 3, 4, 5 minutes, something like that. Because you still have to solve for the C1 and C2 at the end. I'll keep trying to plug that the benefit sometimes of using Laplace transforms is that at the very least, you don't have to do the C1, C2 thing at the end. It's already built in. But anyway, okay, so that's the solution for the problem. Okay, so partial fractions, right? You can certainly use those. I'll give you a slide at the end of this that's sort of a when do I use A versus B. But I want to get to this second method here. So partial fractions, that's one strategy that you can use when you need it. But I said there were 2, and the second one, which I think you've also seen, is known as completing the square. And that's going to definitely be used in order to get us to rules 6 and 7. So first, let me just give this to you algebraically. So if you have a degree 2 polynomial, S squared, I'm going to choose C and D instead of the usual a and b, right? But just a regular old polynomial, right? So now, of course, I have a 1 in front of my s squared, which if you didn't naturally, you could factor it out so that you had a 1 there. But let's just say that I'm here, which is where we were in the last problem, right? I had something like this in the last problem. However, what's different about this one and the one we just did, right? I had, whoops, where am I? Here I am, right? I had s squared minus s minus 2. So that's something like what we're talking about right now. But this one was nice because it factored. But the question is, what do you do if it doesn't factor? And the answer is here. So if you have it like this, if it factors, if you have a degree 2 polynomial in the denominator. I mean, this works even if you're not talking about doing Laplace transforms, but we're going to use it in this sense, right? So you're doing this Laplace thing, you get this ODE, you do the transform, you rearrange the stuff, and when we're on our mission to use the chart in reverse, as we've been getting better with, if you end up with a situation where you have something like this in the denominator, right? S squared minus plus CS plus D. C and D are just numbers. And here, if it factors, you should probably use partial fractions, because we just saw how well that worked. Maybe not our favorite thing to do, but it works. But what do you do if it doesn't factor? If it doesn't factor, though, we can rewrite it as following. So you have this thing, and we're going to rewrite it as, let me get the lettering to match what's in the chart, a squared and b squared. Now, fact, you will always be able to do this. You will. And I'll show you exactly how to do this. If you want, you can derive little formulas for each of them if you're dying to, but anyway. Why would we do this, right? I mean, this seems like completing the square is like a dumb trick unless there's actually a good reason for it. Well, if I could write this, right, so the denominator of my big fraction that I have, if it's unfactorable, I can't factor to do partial fractions, I'm stuck because the chart doesn't really have much for me unless I have one of those formats. Well, notice, one of the formats, if you can't factor and back up to rule 2, I could do these, but again, I'm in trouble because I have an S term. But look at these. 6 and 7 are perfect. They're asking for it, actually, to be in exactly this format. All right, so this is perfectly made. If we could, and this isn't an if, you will be able to rewrite any polynomial like this. You can write it as this, which means it's going to be in the perfect shape to be a rule 6 or 7 in reverse. Okay? So how do we do this, right? Or how do you rewrite it? Well, there isn't much to this. I'll give you the little, in general, I'm not even a big fan of trying to do any sort of memorize thing here. Just sort of say, okay, well, whatever I've got, if I'm going to write it like this, well, what do you get over here? If I multiply this out, I could FOIL this first one, and I get s squared. Well, that's perfect. That matches already. In the middle here, you get 2as, and you get a squared, and you get b squared. That was already there. So in terms of doing our usual matching game thing here that we like to do, let's see. I'm just going to throw parentheses around this to group it. You need a 1 in front of this, and you need a 1 in front of this. Check. Got it. Got it. So that's a freebie. Those are already lined up. Now the S term on the left is C. The S term on the right is negative 2a, which simply means those have to match. So we must insist that, what do we have here? Negative 2a BC, or in other words, A has to be I mean, if you're dying for a formula, it's negative 2 over c over 2. I would honestly say just do this out for each example and don't necessarily rely on a formula, but it's up to you. Okay, and then my third match says over here, whatever was over here, the d that was over here, that's got to be a squared plus b squared. So that's going to tell you what b is. And you'll already know what a is, right? So the other thing I know is that d has to be a squared plus b squared, which tells you b is, what is that? So b minus a squared. It's the square root of that. Or to be honest, let me give it to you this way. You're trying to make it b in the form b squared, so you don't really actually need b. You really just need b squared. So but we make that look a little nicer. It's just d minus a squared. And of course a you already know is that. Okay, this is what I mean. This is offending my senses already, that there's all these letters and things floating around. So I don't necessarily advocate for you to make a big fuss about formulas. If you're dying for them, they're here. But just write it down each time. That's what I'm going to do in the example I'm about to do, is say, oh, okay, how do I complete the square on this? And we're just going to use our brain a little bit. All right. But you will be able to do this. And since you will be able to make the bottom look like this is perfect for rules 6 and 7 in the chart. So we're going to move towards being able to use those two rules when we have to complete the square. When we don't complete the square, because we were able to do partial fractions, we're going to probably end up with something in the top part of the chart, 1 through 5. But when I can't complete when I can't do partial fractions because I can't factor, I'm going to probably have to complete the square, which means I'm heading towards a rule 6 and 7, 6 and or 7. Okay, so let's try one of these and see if we can at least have one to look at and agree that hopefully it makes sense. So here we go. So we have y double prime and 2y prime and 2y, 0, and y, this time we have y of 0 is 0, and y prime of 0 is 4. Okay. Alright, so here's our ODE. Yes, we already know how to do this from before, but let's try this with our new Laplace thing. So again, let me go quickly here. So if I take the Laplace of the whole thing, I once again get s squared Laplace of y minus s times y of 0, which is 0, that's nice, minus y prime of 0, that's 4. Okay, that's y double prime. That's the Laplace of that. Now I have negative 2, so just be careful. Be really careful with these coefficients. This negative 2 has to come along. And now I need the Laplace of y prime, which according to the chart is s Laplace of y minus y of 0, which is 0. Okay, and then the last one is just 2 Laplace of y's. And 0 on the right, Laplace of 0 is 0. Okay, so I take the forward transform, and now I'm going to organize my terms here. So who has the Laplace of y and who doesn't? So if I do that, I get Laplace of y, and let's see, what do I have? I have s squared and negative 2s and plus 2. All right, and let's see. So that's that one. I have 0, and so 4 is the only other thing I have. That's 0 right there, right? S times 0 is 0. So I just have a 4 to go on the right. Okay, so if I swing this down around now, I get 4 over s squared minus 2s plus 2. Okay, now this looks looks somewhat similar to the last one. However, if I try to factor that bottom, we see very quickly that we can't. It doesn't factor. So when it doesn't factor, I think for the most part, it's safe to say, you're going to want to complete the square. So rather than sort of flowing, I might say, let's do a side problem and then we'll come back. So I'm going to complete the square. on the denominator there. So I'm going to say s squared minus 2s plus 2, and I'm going to try to make that look like s minus a squared plus b squared. Okay. All right. Well, in order to figure this out, right, I guess, well, we'll write out what I did a minute ago, right? So this is s squared minus 2as, and then I have a squared plus b squared. So that's got to match that. So maybe it's not totally crazy to, at first at least, to get our thoughts organized, write down what this is, just symbolically. And now I'm just matching. Well, I did a pretty darn good job. I mean, this is already almost perfect. But I think that immediately tells me what? That a is 1. Okay? So that immediately, those have to match, which tells me that a needs to be 1. So I'm halfway there. All right. And now if a is 1, then, let me do it with a box maybe. Those also have to match. So here, let me just reroute my arrow. So 2 has to match a squared plus b squared. But a is 1. So 2 is 1 squared plus b squared. And so 1 is b squared. Okay, so it's easy, right? I mean, this is just a basic arithmetic or algebra thing. So, right, okay. So that tells me that this is really 4 over. Now the bottom, which used to be this, is now the same as this, but with my a and b that I just figured, which both happen to be 1, right? A and b squared. You actually don't need b, right? But b squared is 1. So I'm going to say, oh, you know what? That's the same as s minus a squared plus b squared. You can double check, right, to make sure you got it right. If you FOIL this and then add 1, hopefully you get this, which I think you do. Okay, now this was just a fun exercise, unless this is actually useful. Oh, but wait a minute. One last look at the chart. So remember this, right? So I have s minus 1 squared plus 1. S minus 1 squared plus 1. So if you look at the chart, s minus 1 squared plus 1, that's perfect for 6 or 7 in terms of a being 1 and b also being 1. Right? 1 is, of course, 1 squared. So that's pretty good. Now I have to look to the top, and I have two options. Either you have some s's or you don't have some s's. And the problem we're looking at, I don't. I think I have a 4 up there, right? So I just need to get a b up there, and I will be able to use Rule 6. So the last thing I need to do, I think, before I just do one last step before I'm ready for the chart step. So 1, right, which is 1 squared, I need a 1 on top because it said so, right? It said I'm supposed to have b, and that's supposed to be b squared here, right? That's b squared, and I'm supposed to have a b on top. Well, I have a 4. Well, that's not really what I want. I want a 1 on top in order for it to be b. So I should just factor the 4 that used to be there. Let me just pull that out in front, because once again, numbers, coefficients are easy to deal with. They just come along. So I'm not concerned about pulling a 4 in front of this whole thing. That's fine. So I'm ready for our favorite part, the last step, which says, okay, so y of t is, and then now a coefficient just comes along, so 4 comes along, and then I've perfectly engineered this to be rule number 6, where a is 1 and b is also 1. So rule number 6 would say you should get e to the, I'll just do it for emphasis here, 1t sine of, again, I'll for emphasis do 1t. Of course, right, that's probably just 4e to the t sine t. You don't want to put those unnecessary ones where they belong. And that's the answer. So of course, this hopefully makes sense, or maybe this isn't that surprising. If if you would have done this the way that we did it before, you would have written down the polynomial, you would have found the roots, and maybe you can already tell, well, maybe not, but if you did it that way, you'd find that there are complex roots. So you'd get the e with the cosine and the e with the sine. Now, where's the e with the cosine? Well, apparently when we did the initial conditions, the first one would have turned out to be 0. In other words, C1 turned out to be 0. And C2 apparently turned out to be 4. Okay, that's fine. That happens sometimes. We might have gotten both sine and cosine when we did this, but hey, I'm pretty happy that, that I didn't actually, because it made it a little bit easier. Okay, so I'm going to give you one last slide here with a kind of summary and a little bit of advice as to maybe when and, well, anyway, right, how to decide what to do. And there will unfortunately be some problems where you need to use both. These are the ones where they really start to get pretty hairy, which I'll do an example of next time if I'm feeling brave. But let me at least just give you the strategy of how to know when to use these. So, we have these two tricks now. So when dealing with a fraction of polynomials in general, so we have, I'll just go general here, P of S over Q of S, right? So whatever you got on the top, whatever you got on the bottom. If you can factor Q, then partial fractions, right? You can use partial fractions. If you can't factor Q, then it's pretty much got to be completing the square. So I'll say first thing you want to try, though, is if you can, if Q factors, factor it and use partial fractions to split it up. So in other words, first attempt or first preference is use partial fractions. So if you can factor the bottom, factor it, and split it into two pieces. Now if those two pieces are both good, like in the one we just did, then you can use the chart and you're all done. But there's two places where completing the square might come into play. So do pieces, right? You might need to use completing the square if you're in one of these two situations. Either Q doesn't factor, that's like we just did. Right? So maybe it's the case that you can't factor Q. Okay, then do partial fractions. Unfortunately, the 2b is our worst situation, is that you did factor it, and you did partial fractions, but now you need to complete the square on part or both of your partial fractions. And I say this with disgust in my face that you can't see because I'm not in front of you. I mean, this is what turns a problem into a 30-minute problem, because it's just there's just so many steps then to do, right? So think when we did non-homogeneous problems, right? If you were solving a non-homogeneous ODE from start to finish, I mean, that was pretty involved. You had to do variation of parameters or method of undetermined coefficients, and you had to, there was just a lot of steps. So similarly, that may happen to you here as well. And usually it'll be because you're in 2b. So 2b doesn't factor at all. Or you used partial fractions, so that was good. You did 1. But 1, or I guess if you're really unlucky, both, of the new denominators needs completing. Needs to be completed? I don't know how to say that. Needs completing the square. Not good grammar there, but that's okay. So in other words, you may end up in the worst situation where you started with something, you were able to split it apart, right, into something over Q1 and something over Q2. Well, that was great. But then what if Q1 and or Q2 is a candidate for completing the square? In other words, what if Q1 and or Q2, what if they're not in the chart at all? Then probably you need something. You need some trick. You may need to actually complete the square on those pieces as well, which again is where this really does turn into a bit of a alphabet soup. But I'll do one that's kind of nasty, that sort of has all the things that could possibly go wrong in it next time. But I mean, we're going to try to avoid those at all possible costs because they're just pretty gross. All right. So I think you have everything you need to do for the homework that's posted. I think I put Friday as the due date, Friday the 1st. So check it out. Like I said, after this video, or now, you're good to go. So feel free to go if you get stuck on something, especially a particularly nasty one, and want to wait until the next video to maybe finish up, you can. But I think actually almost all of them, or almost all of them, are actually not that bad. And by that I mean they're like examples that we've done already. Okay, so give them a try, and as usual, stay tuned for more videos this week. And if you have any questions about anything, please let me know, and I'll see you on Wednesday.